Please ask your friends to join immediately. Good morning all. Am I audible? Is the screen visible? Okay, so please ask your friends to join immediately. Okay, let me check. Still, there are only 15 participants. Do you have any placement or internship drive today? Just a minute. I have official call. Hello. हाँ हाँ बोल गो. हाँ 2015च्या आधीचे ज्याला सायटेशन्स आहेत तेवढेच टाकायचे.
क्या कोड है?
Okay, so let us start with today's lecture. Okay, let slide show. Okay, so in yesterday's lecture, we talked about what is deep learning and how deep learning is different than conventional network. So please type your answer in the chat box. Main two differences in conventional neural network and deep learning neural networks. Please type at least one difference between these two, conventional neural networks and deep neural networks. If you don't want to type, unmute and answer this question. yesterday we have talked about these differences, right? So how the deep neural network is different as than conventional neural network. Just a minute. Huh? Okay, so here I got one answer. Deep learning has more layers. Yes, so basically in deep neural network, there are number of hidden layers is much greater than conventional neural network. And one more important difference. What is that important difference? Why those additional hidden layers are required? Those are required for extracting features. So with conventional neural networks, feature extraction, feature transformation, and feature selection, these steps are performed separately. And once you have important features, those are applied to conventional neural network. But in case of deep neural network, even feature extraction is done by the neural network itself. Getting this? So this is main difference. Okay. Now, so additional hidden layers are required to extract the features from the raw data. Okay. So feature extraction is also integral part of the deep neural network. Okay. So in today's lecture, we are going to have a look at some challenges which are faced by deep neural network. Now, so these are various challenges, and one of the important challenge is vanishing gradient. Now, to solve this problem, vanishing gradient, there are two approaches. We can use appropriate activation functions, and we use appropriate weight initialization to solve this vanishing gradient problem. Now, before going to how to solve this problem, let us first understand what do you mean by vanishing gradient. Okay, so now all of you are familiar with this diagram. What this represents? This diagram represents, it is a single perceptron. And what type of activation function is used here? Can you name this activation function? This is a single neuron which performs weighted addition of inputs and weights, and then activation function is applied. What type of activation function is this? Yes, it is step function. You can apply binary step or bipolar step function. So these are this revision is necessary in order to understand vanishing gradient problem. Okay. Then from basic activation function of type step function, we go for next type of activation function, that is sigmoidal function, right? So this is also a single perceptron which gives you net output, which is weighted addition. Then we apply sigmoidal function. This is formula for sigmoidal function to get the, and once we apply this sigmoidal function, we get output from this particular perceptron, final output. We can indicate it by sigma of net, where sigma represents sigmoidal function. Okay. So this is about single perceptron. Now, when we have multi-layer perceptron, like as shown here, when we have a neural network with multiple hidden layers, which training algorithm we use? We use backpropagation algorithm, and this backpropagation algorithm works on gradient descent method. So in this backpropagation algorithm, what are the main three phases of backpropagation algorithm? This revision is needed in order to understand vanishing gradient problem. Okay, so please revise what we studied under backpropagation algorithm for multi-layer perceptron network. And please tell me what are the three important phases of training a network by using back propagation algorithm. What are the important phases? Am I audible to you? Is the screen visible? Okay, so now I'm getting answers. Forward pass, backward pass, and weight updation. Yes, correct. Now during backward pass, what we do? So after completion of forward pass, we get weighted addition output from your final layer, right? We propagate the input forward from input layer to hidden layer 1, hidden layer 1 to hidden layer 2, and then from hidden layer 2 to final layer. Here we get final output after applying activation function. Then what we do? We compare this output with the target value given, and from that we determine the error, squared error term. And during backward phase, we take gradient of this error, and we use that gradient to decide change in weight, right? We propagate that gradient of error backwards from output layer to hidden layer, then from hidden layer to next hidden layer, till we reach to the input layer. We continue this process. So during backward pass, what is important is we determine gradient of error, and we use that gradient of error to decide updation of weights at this layer. Further, we once again take gradient of error, and we determine del terms or change in weight terms for next layer, and we continue the process till input layer. Okay, so this is your back propagation network revision. So during forward pass, this green arrows are followed, and during backward pass, error is propagated backwards in this particular direction given by these dotted arrows, right? So here, what we actually propagate, we take gradient of error because your algorithm is based on gradient descent, right? So gradient of error term is very important in back propagation algorithm, and also it is very important for deep neural networks. Okay, so basically vanishing gradient occurs in a training process of back propagation when output error fails to reach to further nodes. Okay, so here we are propagating that gradient of error from output layer to hidden layer, then hidden layer to next hidden layers, from next hidden layers to input layer, right? So that gradient of error is propagated through the entire network till we reach to the input layer. Now, what will happen if gradient of, say, after certain hidden layers, say when you reach to this last hidden layer, and if this gradient value is very small, it is possible that when you reach to almost your input layer, this gradient becomes almost zero. And what will happen if gradient becomes zero? Is weight updation possible if gradient is zero? Because your change in weight is directly proportional to gradient of error. And if this gradient of error becomes zero, your del term, del W will become zero. Agree? Here, this del W is directly proportional to gradient of error. Now, if at the layers, hidden layers which are closer to input layer, if your gradient becomes very small, and if at certain stage, if it becomes zero, this gradient term will vanish, right? It is zero means your gradient is 0, means del W is 0, because change in weight is directly proportional to gradient value. Now, if this change in weight is 0, your W new remains as W old, right? Because your change in weight term is 0, right? And this is known as vanishing gradient. Because your gradient has vanished, change in weight is 0, and as change in weight is 0, there effectively your weights are not at all updated, because your W new weight value is same as old weight value, and this means your weights are not at all updated for those layers which are closer to input layer, because in deep neural network there are many hidden layers. Okay, here in this picture there are only two hidden layers, and between these two hidden layers these dots are shown. Meaning of these dots is that there are multiple hidden layers. Okay, there are not only two hidden layers, but there are many hidden layers. Okay, and as you move towards input layer, gradient value becomes smaller and smaller, and there is possibility that gradient completely vanishes for those layers which are closer to input layer. And when your gradient vanishes, there is no weight change. So as if you are not at all training these layers which are closer to the input layer. Right? Getting this? Please type yes or no whether you are getting the concept of vanishing gradient. Okay, so there are few students who are not getting the concept. I think with further explanation, it will be clear to you. For most of students, for many students, I have received yes answer. So now let us go to further details. So why gradients vanish, that now we are going to study. Yes, because of some reason, there is possibility that gradient value becomes very small, and at certain instance it is possible that for the layers which are closer to input layer, it completely vanishes and there is no weight updation. And when there is no weight updation, means those layers are not at all trained. Now let us try to understand why the gradient vanishes. Okay, what are the reasons behind this? Okay, now let us have once again look at sigmoidal function. So this is your sigmoidal function where output varies between 0 and 1, right? This is your graph for sigmoidal function. This sigma x is given by 1 upon 1 plus e raised to minus lambda x, and lambda is usually considered as 1. So it is written as 1 upon 1 plus e raised to minus x. So basically, these are properties of sigmoidal function. Sigmoidal function compresses all its inputs to range between 0 and 1, right? Then a sigmoidal neuron is said to have saturated when sigma x is 0 or sigma x is 1. Okay, so on these two ends, this is one of the extreme and this is another extreme. So if you look here, sigma x value is 0 and here sigma x value is 1. And this is known as saturation condition because output cannot go beyond 1 and similarly it cannot go below 0. So this state is known as saturated state. Now how we derive a gradient of sigmoid function? If you perform mathematical derivation operation, we get this gradient of the sigmoid as sigma x into 1 minus sigma x. We have studied it in previous initial lectures. Okay, so this is simple derivative operation. If we apply derivative on 1 upon 1 plus e raised to minus x, we get this equation sigma x into 1 minus sigma x, right? So this is gradient of sigmoidal function. Now tell me, if we consider this lower extreme value or lower condition of saturation, what is gradient value? If your sigma x is 0, what is gradient value? Substitute 0 in this equation. 0 into 1 minus 0. So here you are getting gradient value as exactly 0, right? Similarly, if you consider other extreme, if your sigma x is 1, what is gradient value? Type your answer in the chat box. If sigma x is 1, what is gradient of sigmoidal function? Substitute 1 in this equation. What is gradient value for sigma x is 1? Please type your answer. Yes. So if you substitute sigma x as 1, here you will get term 1 minus 1, 0, 0 multiplied by 1. Ultimately, you will get 0 value for the gradient. Yes. Okay. So here, once if we consider two extreme cases, sigma x is 0, sigma x 1, we get gradient value as 0. And when gradient is 0, it means your gradient have vanished. Okay. And when gradient vanishes, there is no weight of updation. Okay. So if your net output is very high, right? In this, the x-axis represents weighted addition from the neuron or the net output, right? So if your net output is very high, in that case, you will get your neuron in saturated state because sigma x is 1. And when sigma x is 1, your gradient value that you are getting is 0. And it is treated as dead neuron because when gradient becomes 0, weight updation is not at all taking place, right? So if your net output is very high, you are getting gradient value 0. Similarly, if your net output is high in the negative direction, right? Uh, or it is very low, you can say. If it is very low, then also gradient can vanish, okay? Because when it is very low, sigmoidal output is 0. And when sigmoidal output is 0, gradient is 0, okay? So for both extremes, there is possibility that gradient vanishes. And when gradient vanishes, it's not possible to update weights, okay? And there is effectively no training, okay? So saturated neurons thus cause the gradient to vanish. Now let us have a look at why neurons get saturated. Why it can take output 1 or 0. It is when your net output is very high or very low, your gradient can vanish, right? I request all of you to switch off videos. Please switch off your video. Okay, thank you. Okay, so basically, if your net output is very high or very low, then you get dead neurons or you get saturated neurons. So sigmoidal function is one more reason why sigmoidal is not very good, because sigmoidal function is not zero centered, because here your output is either 0 or 1. It is not symmetric around 0. That's why it is not zero centered. Then either all the gradients at a layer are positive or all the gradients at a layer are negative. Now as sigmoidal is not zero centered, there is all the gradients at particular layer, they either increase in positive direction or they decrease in negative direction. It also depends on what are your initial weight values, okay? And that's why output of sigmoidal is always either positive or negative, and this restricts the possible weight update direction. So your weight updation is either always in positive direction or it is in negative direction. And one more drawback of sigmoidal is computationally expensive. Why computationally expensive? Because for every neuron you need to compute this term 1 upon 1 plus e raised to minus x. For every neuron, your input x is different. For hidden neurons, your output from previous layer for every neuron is different. So you need large amount of computations. Okay. So when we are using sigmoidal function, there are these drawbacks. It is not zero centered. Weight updation direction is restricted, and it is computationally expensive, and it can lead to vanishing gradient problem if your net output is very high or very low. Okay, so that's why we can think of some other function for avoiding this vanishing gradient problem. So another case is dan h hyperbolic tangent function. Okay, so as compared to sigmoidal function, here one problem is solved, that is it is now zero centered, right? This dan h function varies from -1 to +1. So now your output is zero centered, right? So this one problem is solved. Now let's see whether vanishing gradient problem is solved to certain extent by the dan h function. Now all of you are familiar with this dan h function. It is given by e raised to x minus e raised to minus x divided by e raised to x plus e raised to minus x. Now if you determine derivative of this function, what you get is 1 minus dan h square of x. Okay, dan hx square, right? This is derivative of dan h function, 1 minus your fx or dan hx square. Okay, so this is derivative. Now let us consider whether this derivative term gives you vanishing gradient or not for the extreme cases. Okay, now say if consider this extreme side where your neuron is saturated. Now for dan h function, when your net output from the neuron is very high, you get output as shown here, which is 1. Okay, now if we consider this case, that is dan hx is equal to 1, substitute this value here, 1 minus 1 square. So 1 minus 1 square results in 0, right? So for this side, there is possibility that you get a dead neuron, right? Because here you are getting gradient output as 0. 1 minus 1 square gives you 0. Similarly, if you consider other extreme, here other extreme, when your net output is very high in negative direction, again output is -1, right? So when output is -1, again if you substitute this -1 here, 1 minus -1 square is again +1, 1 minus 1, this gives you 0 gradient value, right? Derivative is nothing but your gradient. Okay, so this vanishing gradient problem can take place also for dan h function. For one extreme, for positive extreme or for negative extreme, you are getting dan h output as +1 or -1, and when it is +1 or -1, its gradient value or derivative value is 0. So the gradient still vanishes at saturation levels. Again, like sigmoidal function, it is also computationally expensive. There are more number of e raised to x terms and additions and subtractions of e raised to x terms. So it is computationally expensive than, it is more computationally expensive than your sigmoidal function. Okay, so in order to solve vanishing gradient problem, then H function is not useful like sigmoidal function. So one more activation function is available which is useful for deep neural networks, that is the rectified linear unit. And you might have heard this short form RELU in your project works or in your internship works. You might have used this RELU function. Okay, so this RELU stands for rectified linear unit. Now let us see whether this RELU function resolves your vanishing gradient problem. So this RELU function is as shown here. If your net output from the neuron, if it is greater than 0, there is linear relationship between fx and x. Okay, so your fx is nothing but x when your output is greater than 0. And when net output, that is weighted addition term from a neuron, when it is less than 0, output of ReLU function is 0. So this graph shown in blue color that represents your ReLU function. Its equation we can write as f of x is equal to max of 0 comma x, right? So if your say net output is -2, okay, so x is -2. What is max of 0 comma -2? Maximum of the two, it is 0, right? So when your input net output from a neuron, that is weighted addition, when it is equal to -2, you are getting output of this ReLU function at 0, because we are using simply maximum operation. We are comparing 0 and x, or we are determining maximum between 0 and x. So if x is negative or if x is less than 0, maximum will be 0. And if x is positive or if x is greater than 0, we are your fx is same as x. Okay, fx is same as x. This is your rectified linear unit or activation function ReLU. Okay, and as the relationship is linear, the name is linear unit, and rectified because it is useful for rectifying vanishing gradient problem. That's why the name is given as rectified linear unit. Okay, so basically this function does not saturate in the positive region, right? If you look at the positive region, there is linear relationship. So as your x increases, fx increases. Means as your weighted output from a neuron increases, fx increases, right? So on positive side, this ReLU function does not give you saturated neuron. Then as compared to sigmoidal or Danish function, this is computationally very efficient. Can you tell me for this ReLU function, how many computations are needed for a neuron? Do you need any addition, multiplication, exponential operation to determine fx from x? No, you don't need any multiplication, addition, or exponent operation. But what you need simply one comparison operation at every neuron. You need to compare x with 0, right? So it is computationally very, very efficient than your Danish function or sigmoidal function. Okay, so this ReLU is computationally efficient. It also gives you, it doesn't give saturation in positive region, and in practice converges much faster than sigmoidal or than H function. So when we use ReLU function, network convergence is faster at a higher speed. Okay, now let us talk about gradient. What is gradient of this particular region? If this is linear relationship with fx same as x, slope is always 1 and slope is nothing but the gradient or derivative of your function, right? So this slope is for when your x is greater than 0, gradient of ReLU function is 1, and when your x is less than 0, gradient is 0. Okay, so this is gradient value. Now if we consider this side where x is greater than 0, is there possibility of vanishing gradient? Is it possible gradient takes 0 value? It is not at all possible, because irrespective of x value, gradient value is always 1. So on one side, that is positive side, if your x is greater than 0, this problem is resolved. Vanishing gradient problem will not happen at on this side if your x is very large. But for other side, that is if your x is negative, still there is possibility of vanishing gradient. Why? Because gradient on this side, if for this ReLU function, is always 0. Gradient value for ReLU function, if your x is less than 0, is 0. So we can say that vanishing gradient problem is solved to certain extent by this rectified linear unit, right? So there is one question, ma'am, but for x less than 0, its value will be 0 and gradient will be 0. Yes, Ajay, that's what I'm explaining you. So we can say it is this vanishing gradient problem is solved to certain extent, because on like with Danage or sigmoidal function, gradient was vanished on when your output was high, neuron output was high. Now that is not happening with the ReLU if your neuron output is high on positive side. But still there is problem with ReLU for smaller outputs from neuron. If your output from neuron is negative, still there is vanishing gradient problem because gradient value is 0. Okay, so let us see what is remedy for that. Okay, so basically before going to solving that problem, if at some point in a network a large gradient causes the bias B to be updated to a large negative value, so the same problem we are discussing here. If your bias value is very high in negative direction, your W1 x1 plus W2 x2 plus B, this will result in a value which is less than 0. Okay, so the neuron would output a 0, means it is a dead neuron because gradient value is 0. Okay, so the weights W1, W2 and B will not get updated in back propagation. Okay, so in practice, a large fraction of ReLU units can die if the learning rate is set too high. Okay, so even this your deep neural network with ReLU function can face problem of vanishing gradient if your learning rate is high. If your learning rate is very high, there is possibility that bias term is takes value which is large negative, and if one of the term is very large negative, total output from a neuron can go below 0. And when total output from neuron is below 0, gradient value is 0. Okay. So even with ReLU, we can face problem of vanishing gradient. Okay. So we have another option, that is leaky ReLU function. Now why it is known as leaky? Because for negative side, now instead of 0, it is giving you small linear output. Okay, that's why as this is giving small output, It is known as leaky ReLU function. Okay, now if you look at this portion, so this is your leaky ReLU function, and you can model it mathematically as shown here. Your fx is maximum of 0.01x comma x. So slope for this particular portion, when your x is negative, here slope value or gradient value is 0.01 instead of 0. Now we have gradient value of 0.01. So this leaky ReLU does not saturate on positive side, and it also does not saturate on negative side, because it guarantees small gradient value because of this slope parameter of 0.01. Okay, so there won't be saturation. Your neuron will not die. 0.01x ensures that at least a small gradient will flow through the network in backward direction. Okay, and still it is computationally efficient. Again, tell me how many computations are needed at every neuron. Actually, you need very less computations. You simply need to multiply your input x by 0.01 for negative values of x. For positive values of x, you don't need any computation, because your x, y is same as x, or f of x is same as x. So on negative side, you need one multiplication multiplying x by 0.01. And as a total function, you need one more operation, that is comparison. Compare 0.01x with x. Okay, so again, this is as compared to sigmoidal or Danish function, this is computationally very efficient. Okay, and it solves your saturation problem on positive side as well as negative side. And again, as we can say, it is close to zero centered output. It is not exactly zero centered, but it has some positive part, it has some negative part which is centered around zero. So we can say that this is close to zero centered outputs. Okay, so because of these advantages, in deep neural network, leaky ReLU function is used. Now, this leaky ReLU function we have talked about just now is given by maximum of 0.01x comma x. Now this function you can generalize by using alpha in place of 0.01. Okay, and when we use here alpha, the same leaky ReLU function is now known as parametric ReLU. Here, why parametric ReLU? Because this alpha can be treated as one of the parameters. So we can write this parametric ReLU as fx is equal to max of alpha x comma x. If we initialize alpha to 0.1, we get this specific case. Okay, so this parametric ReLU is given by fx is equal to maximum of alpha x comma x. Now, why this is known as parameter? Because during training process of deep neural network, you can use this alpha as one of the trainable, one of the parameter which you can vary for every epoch. For initial epochs, you can have greater value of alpha. Okay, so for initial epochs, instead of this slope of 0.1, you can have slightly greater slope. Say you can have slope of 0.08, etc. Okay, so 0.08 or 0.1 instead of 0.01 for initial epochs. Okay, and as you move from first epoch to second, second to third, for every epoch you can reduce this alpha value. Okay, so that you can guarantee that the gradient will reach till your input layer. Okay, so and at the same time, for initial epochs, higher value of alpha means you can take greater step size. Okay, higher value of alpha means greater step size, and as you approach to the solution, you can reduce alpha value so that step size becomes smaller and accuracy increases. Okay, so this is known as parametric ReLU. Here alpha acts as one of the parameter that you can update during your back propagation training. For every epoch, you can update it. Or say after certain epochs are elapsed, you can reduce this alpha value. Okay. And in most real applications with deep neural networks, this parametric ReLU is used. Okay. There is one more variation of parametric ReLU, and it is known as exponential linear unit. On positive side, it is linear, and on negative side, it is exponential. So here, instead of direct linear region for the leaky portion, here exponential value is used. So it gives you all benefits of basic ReLU function, and this leaky portion, which is given by a into e raised to x minus 1, it ensures that at least a small gradient will flow through the network till your input layer. Okay, so even with exponential linear unit, exponential ReLU, your vanishing gradient problem is resolved. Okay, and again it is approximately close to zero centered outputs. There is, for positive part you have this linear portion, for negative part you have this exponential portion. So we can say it is approximately zero center. Okay, so the equation for exponential linear unit is as shown here. Fx is equal to x if x greater than 0, and it is equal to a into e raised to x minus 1 if x is less than or equal to 0. And again this a can be treated as a parameter, okay, which you can update during the back propagation training. Okay, so this is about how we can solve the problem using ReLU or exponential ReLU or parametric ReLU, leaky ReLU, parametric ReLU, and exponential linear units. With these units, we can solve vanishing gradient problem by using these three types of activation functions. Now, there is one more important parameter that might lead to vanishing gradient, that is your weight initialization. So what weight initialization strategies you are using, that is very, very important. If your weights are very high, that can lead to vanishing gradient if we are using sigmoidal or dan H function. Similarly, if these weight values are very low, it might lead to vanishing gradient problem. Okay, so we will talk about what are the weight initialization strategies when we are using sigmoidal or dan H function to avoid vanishing gradient problem. We will discuss this in the next lecture. Now I request all of you to type your roll number and name, and if you have any queries related to basic understanding of concept of vanishing gradient and concept of these activation functions, please ask your questions. ReLU, leaky ReLU, and parametric ReLU. Okay. So if you don't have any question, please type your roll number and name and you can leave the meeting. Okay, thank you all.
Ma'am, our group had a question assignment.
Okay, bolo.
Ma'am, so our topic is RBF applications and the comparison with other methods.
Okay.
So we found a topic for stock market predictions, but it is a class classification problem, which will tell if the if the prices go high or low.
Okay.
So research paper, instead of backprop, they have used another algorithm called ELM, which is extreme
Okay.
learning machine.
Okay, very good.
The research paper is around that, so can we go ahead with that?
Yes, yes, sure. Because your main intention is you should learn something extra. Okay, so if you are
Yes.
having different algorithm, it's very good. Okay,
Okay.
you will get a
Ma'am,
chance to
like,
study that another algorithm. At least try to understand it at conceptual level. Though all mathematical details are not clear, try to understand how it is different than your back propagation algorithm. Okay.
okay, ma'am.
Ah,
Ma'am, and
ah.
like, are there any specific comparison points that we need to consider, or
No, that
like,
option is given to you. Okay.
okay,
Wha-
yes, ma'am, got it.
How much possible depth, how much depth you can go, try to reach to that depth. Okay.
Yes, ma'am, understood.
Okay. And I have already given format of this assignment, how you have to write that survey that is available on Teams platform. Okay.
Yes, ma'am, yes, ma'am.
Okay. Thank you, Revati.